All right, welcome back. Today we are diving into a story about one of the biggest challenges in tech right now. It's all about teaching computers to predict the real world and do it in real time. But here's the kicker. How do you build an AI that's not just smart, but literally fast enough to keep up with reality itself?
No, seriously, just pause and think about that. What if a simulation running on a tiny little chip inside your car or out on the power grid could perfectly mirror what's happening in the physical world and do it instantly? I mean, that sounds like something out of a movie, right? But it's not. It's the goal driving some of the most mind-blowing AI research happening today. And the secret to making it all work? It's a concept called edge computing.
So what exactly is edge computing? Well, think of it this way. It's all about doing the heavy lifting, the number crunching, right where the action is happening. Instead of, collecting data, sending it off to some huge cloud server miles away, and then waiting for an answer to come back, the thinking happens right there on a small local chip. And for things that need to react in a split second, this is absolutely crucial. This is the stage where our whole story unfolds.
Okay, so we've set the stage. We need fast, local intelligence. But trying to run these incredibly complex simulations at the edge, well, it throws up a huge wall. And to really get why, we need to pop the hood on our modern energy systems.
Right at the heart of it all are these things called power electronic systems, or PES for short. Honestly, these are the unsung heroes of our world. They're managing the flow of energy in pretty much everything we touch, from charging your phone to powering an EV, all the way up to keeping the entire electrical grid from collapsing. And simulating them with perfect accuracy, well, that's the core of the whole challenge.
See, on the one hand, their behavior seems kind of predictable. You've got energy flowing in these nice, smooth ways, almost like a wave. And engineers have a language for this. They use what are called ordinary differential equations, or ODEs, which are basically the standard rulebook for physics. But, and this is a big but, these systems are also defined by switches. Tiny switches flipping on and off thousands, sometimes millions of times a second. And every single time one of those switches flips, it creates this abrupt, instantaneous jump in how the system behaves. So you've got this mix of smooth waves and these super short, sudden jumps. That combination is called hybrid dynamics, and it is what makes simulating these things in real time an absolute nightmare.
And this right here, this is the dilemma. The tools we've traditionally used, these classic simulators, they are just way too slow. They're clunky, they're resource heavy, they just can't keep up. But at the edge, where we need this to work, you need the total opposite, something ridiculously fast, super efficient, that can run on a chip the size of your thumbnail. So how on earth do you build that?
This brings us to our first hero in this story, a breakthrough AI approach that was designed for one thing and one thing only: pure raw speed. The researchers gave it a cool name too, the Neural Substitute Solver, or NSS for short.
Now, the way the NSS works is really clever. It's not just one AI. It's a team of two specialized neural networks working together. The first one, the Model NN, is like a genius assistant who has basically memorized all the hardest, slowest parts of the math and just spits out the answer. Then the second one, the Solver NN, acts like a brilliant supervisor. It lets a really simple, fast calculator take these enormous leaps forward in time during the simulation without messing up the accuracy. It's a tag team approach.
And the results of this tag team? A truly massive speed up. I mean, it's not just a little faster. The Neural Substitute Solver ran the simulation, get this, 23 times faster than the traditional method. For anything that needs to happen in real time, that's not just an improvement, it's a total game changer. But here's the crazy part. It's not just faster. It's also way, way more efficient. When they put it on one of these programmable chips, the kind you'd actually use in an edge device, the NSS used, on average, over 60% fewer hardware resources. So it's faster and it's smaller. Problem solved, right? We've got the speed we need. Well, not quite, because this victory actually uncovers an even deeper, more fundamental problem. So yeah, we managed to get incredible simulation speed. But that just begs the next question. How close is our super fast simulation to the real thing? And this question brings us face to face with what's known as the sim-to-real gap. And here's the heart of the gap. On one side, you've got your pure physics models. They're great in a perfect textbook world, but they have no idea how to handle the messy, real-world stuff, like a component getting old and tired or the circuit heating up. Then on the other side, you've got these black box AIs. They can learn patterns from data, sure, but they have zero understanding of the actual laws of physics. That makes them kind of unpredictable, and they need just mountains of data to learn anything useful. So neither one is the perfect solution. Clearly, what we need is a new way of thinking, something that can combine the best of both worlds. You know, the strict rules of physics with the learn-on-the-fly adaptability of AI. And this is where our second solution, the hybrid, comes into play. This new approach is called Physics-Embedded Neural ODEs, or PENODE, and the idea behind it is just beautiful. Okay, imagine you're building a flight simulator. Now, instead of asking an AI to learn the entire concept of aerodynamics from scratch, which is insane, you give it the physics textbook first. You tell it about gravity, about lift, all the known rules. Then you ask the AI to do the much smaller job of just learning the unpredictable stuff, like random gusts of wind. That's exactly what PENODE does for electronics. So the AI's job becomes so much simpler. It's not trying to figure out the whole system anymore. It's just learning what they call the residual, that little bit of difference between the perfect physics model and what's actually happening in the messy real world. You know, things like that component wear and tear or those temperature changes we talked about. This makes the AI laser-focused, and as a result, way more efficient and accurate. And if you look at how this stacks up against other methods, you can see why PENODE is so special. Other hybrid models might treat the physics part and the AI part as two separate things, kind of bolting them together. But PENODE, as you can see there in that bottom row, it deeply weaves them together. It trains the known physics equations and the AI's learning process all at once, from end to end, letting them work together to find that perfect balance. And the payoff for this hybrid strategy? It's just incredible. Because the AI has a much, much smaller problem to solve now. The final PENODE model needs 75% fewer neurons than a comparable black box AI would. Let that sink in. It's not only more accurate and grounded in real physics, it's drastically, drastically simpler. Okay, so let's put this all together. We have the lightning speed from our neural substitute solver, and we have the incredible reality-based accuracy from PENODE. So what? What does this actually let us do out in the real world? Well, this combination of speed and accuracy, it unlocks a whole new universe of possibilities. We're talking about more efficient electric vehicles that can literally optimize our own battery usage mile by mile. We're talking about smarter, more resilient power grids that can predict problems and fix them before a blackout even happens. We can finally build what engineers have dreamed of for years: true digital twins, perfect, living, virtual copies of physical systems. But maybe the most jaw-dropping impact is on control. Right, because these models are so fast and so accurate, you can use them to actively control the very systems they're simulating. Now, with the old way of doing things, if you wanted to, say, change the power output, you'd get this slow, gradual adjustment. It might take several cycles for it to finally settle down where you want it. But with a controller that's being guided by one of these new AI models, the response is almost like magic. The system predicts the exact perfect adjustment it needs to make and just does it instantly. It hits the new target within a single tiny switching cycle. That is the power of having a perfect real-time model running right at the edge. So think about the journey we just took. We started out just chasing pure speed, and we found it. But that amazing breakthrough led us to an even deeper challenge. How do we close that gap between our simulation and reality itself? By embedding real physics directly into the heart of AI, we're creating digital models that are not just fast, but are becoming astonishingly accurate. And that leaves us with one final and really exciting question. As our digital models get closer and closer to being indistinguishable from the physical world, what incredible problems are we going to solve next?